So we remember that oxidation of primary alcohols gives you aldehydes, oxidation of aldehydes gives you carboxylic acids. We can use that as a test for aldehydes because if we had a secondary alcohol, we oxidized that, it would make a ketone, and you can't oxidize ketones. So we can have a distinguishing test for aldehydes and ketones by coming up with a fairly mild oxidizing agent. So it'll only just work on aldehydes and nothing else. That's kind of the key there. So our two mild oxidizing agents are, yes, Melvin?
Potassium dichromate.
Well, that will work, yes, but potassium dichromate in acid, obviously, has the disadvantage of being a bit too good. It's quite strong, and it will oxidize alcohols as well. We want something that will only just oxidize aldehydes, so we use a couple of very specific substances. Test for aldehydes. We know that Andy knows. One. Tollens. What is tollens? What's tollens? That's good. That's good. Friends, you're all late. You're late on camera as well. Everybody at home will be able to see you shuffling in at 8:56. See me have to break from my lesson to put you in the wrench. How selfish. Charlie. Zion, don't sit there chatting, having come in late. You're on point now. Tell us all about Tollens reagent.
Is it for aldehydes and these for silver?
Good, well done. Thanks for catching up. Now, can you actually tell us what it is?
Is it a reagent?
Yes.
No,
I mean, I don't have a big bottle next door labeled Tollens reagent. If I want to test with Tollens reagent, I'll make it up myself from ingredients. What are those ingredients?
is it nitrate?
Sorry?
Does it have nitrate in it?
Yes, nitrate's not really the important bit of that substance.
I don't remember.
You don't remember? You better pay attention then and stop talking. Kobe, any ideas? Silver nitrate, okay, good. And what else goes into it?
What as well as so it's not just the tollens, or is this to make the tollens?
To make the tollens, you use silver nitrate. Bit of something else. No. The opposite. Go on. Yeah, it's got ammonia in it. So it's sometimes called ammoniacal silver nitrate. You can call it that if you want. I'm imagining you'll be happy with Tollens reagent. But it's a complex of silver and ammonia. Ammonia molecules, NH3, hence the plus charge. Okay. Just to keep things simple, I'm going to write silver just as an ion. What happens to it? What happens when we use silver nitrate. Becomes a silver mirror. Very nice. So, what half equation would I write for that? Okay, Eddie, can you fill us in, thanks?
Silver ion becomes, you would add an electron.
You would add an electron and make.
Solid element of silver.
Great. Okay. Okay. Yeah. So we got our silver mirror. Looks a bit like this. Here's one I prepared earlier. So that's just a flask with some aldehyde in it, swirled around some Tollens reagent, and made a nice mirror flask.
Pretty
There's on top of my Christmas tree.
Yeah.
No, it really does.
Do that. So
The other, don't drop it. You know how Christmas decorations are always fragile. The other reagent, Charlie, that we can test aldehydes with? Phalings. For some reason, I don't know why, it's always Phalings solution, but it's always Tollens reagent. I don't know why. Surely you could have Phalings reagent as well, but it isn't. What is Phalings solution reagent stuff? What's in it? What colour is it? Blue. Okay. What blue solutions do we know from chemistry? Copper. Yeah. So, do you know what else is in it? It usually does get brought out as Phalings A and Phalings B, or as Benedict's, of course. It's the same stuff, but it's alkaline copper 2+. And again, the alkaline is there to kind of moderate the oxidizing agent, make it a bit weaker, really. So it'll only just oxidize aldehydes. Okay. What does it form? Does it form, Matty?
Cu plus with 1 plus.
No, I can't do that, I'm afraid, because it's a solid. What does it look like?
It looks like a brick red precipitate, doesn't it?
Brick red precipitate. Great. So we've got a blue solution, forms a brick red precipitate. That was a silver mirror. Of
Is it CuOH?
no. That's silver. That's copper 1, isn't it? I suppose. Yeah.
Couldn't tell it.
No. Toby. No, it is. Brick red precipitate of. Eddie.
Does it involve the Cu3 plus ion?
Cu plus. No. Cu plus.
3.
It's been reduced. Yeah.
Yeah.
We're going from copper 2 down, so it can't go up to 3+, it has to go down to 1+. Well, we'll come to the electrons in a moment. Let's get the product first.
It's not copper carbonate, is it?
It's not copper carbonate, no. No, copper 1 oxide. Cu2O. Okay, can you balance that half equation, please?
Yeah, I said H2O on the left side. Also I did 2C2 plus and 2H plus on the one side. So then I said it was just E minus on the left.
Grand? Okay, that's all fine, except you can't have H plus in a balanced half equation when we're in alkaline solution. But there's a fix here, and it's a sort of mathematical fix. In that if you add something to both sides of a maths equation, it doesn't change the equation, right? Because it cancels out. So what I do, I've got two H pluses to get rid of. I add two OH minuses to both sides. Hasn't changed the equation, just added two OH minuses. OH minuses and H pluses cancel out to make okay. Anything else needs to cancel?
Oh. There's one water in the left side and two on the right.
Okay. So there's my finished equation. This is a standard fix, by the way. If you ever have to balance a redox half equation in alkaline conditions, you do it for acid first and you balance it for H plus because you've done that 100 times and you know how to do that. And then you add OH minus to both sides to cancel out the H plus. So if I get rid of all of that, make it a bit tidier, that's now H2O. And over here, we've got 2 OH minus. There we go, and it's all balanced. Super fine. Okay. So those are the two standard reagents we use. You can, of course, also use, that's up on here, isn't it? We're on freeze. You can use potassium or sodium dichromate in acid. That will work. You just have to know your colour changes for this. Because we've got our blue solution becomes a brick red precipitate here. What's the colour change if you're using dichromate with acid? Yeah, it starts off a really kind of bright, livid Lucozade orange, and then it goes a nice, gently kind of green or greeny blue. Do you know what the greeny blue is? It's Cr3+. So you're reducing chromium 6 down to chromium 3, and that gives you that green colour. Okay, so you can use that in your chemical tests as long as you know the orange turns to green. Okay. Yeah. Excuse me. Right. One more thing while we're doing oxidation, and again you might have covered this last year, but it doesn't hurt to reinforce it. If I use acidified potassium dichromate to make an alcohol into an aldehyde, and I use acidified potassium dichromate to make an aldehyde into a carboxylic acid, if I just want to make the aldehyde, how do I get an alcohol to kind of stop halfway? If I don't want to make any carboxylic acid, I just want to make the aldehyde, how do I make sure the reaction doesn't go any further? Yes, Mel? Distillation. Okay. So yeah. So standard apparatus for distillation. Thermometer there. So in here I'd have my reaction mixture, whatever it is, the alcohol and the oxidizing agent. There it is. bubble, 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 and then I just keep the temperature just below the boiling point of the aldehyde. But hang on a minute, why will the aldehyde distill and not the alcohol that we're starting with? Isn't there a danger that I'll just distill over the alcohol as well? How do I stop the alcohol from distilling?
Would you use reflux so it drips down?
No, if you reflux, you'll get the carboxylic acid. We'll hold that thought. We'll come to that in a moment.
What was the question, sir?
The question is, why won't this distill over alcohol as well? After all, I've got a flask full of alcohol, right? Go on.
Because the alcohol reaches boiling point.
Right, boiling point is the right answer. Tell me about the boiling points of alcohols versus the boiling points of aldehydes. Because
Alcohol hydrogen bond.
right, that's it. Because the alcohol has an OH group in the molecule, it'll have hydrogen bonding. And hydrogen bonding, as we all know, is the strongest type of intermolecular force. The aldehyde, it has O and H in it, of course, but not attached to each other, so it doesn't have that big difference of electronegativity that you get in an OH group, so it can't hydrogen bond. So it's, permanent dipole forces, whatever, a bit of van der Waals, but it doesn't have the strength of the hydrogen bond. So the boiling point of an aldehyde is always going to be lower than the boiling point of its respective alcohol, the alcohol it's made from. Okay, great. So if I heat it up, if I keep the boiling point just below or between, really, the alcohol, boiling point, the alcohol and the aldehyde, that should be perfect. The aldehyde will distill, the alcohol won't. If I want to make the carboxylic acid, from the alcohol, this is where your answer comes in, Matty. If I'm starting with an alcohol and I want to make the carboxylic acid, I don't want any aldehyde left in the game.
So you've got to make it drip down first to get to it's oxidised twice.
So we use this apparatus, what did you call it?
Reflux.
Reflux. So rather than fitting the condenser so it'll remove stuff, we fit the condenser so it'll return everything back to the flask. There's our mixture of alcohol and oxidizing agent in there. Bubble, bubble, bubble. It'll evaporate up, cool, condense, and drop straight back in. So any aldehyde that we make will get returned to the flask and it'll keep churning over and over with more oxidizing agent until it's turned into carboxylic acid. So we leave that for half an hour or whatever time period and just wait for the carboxylic acid to be formed.